Hi everyone and welcome back. Today we're going to talk about the system design of the distributed LRU cache. We're going to take Memcached as an example and talk about how they would implement a cache from scratch. So we're going to start out with talking about the data structures, how it would utilize them. We'll talk about the different aspects and locking on those data structures and how we can improve them to increase the throughput of the cache. We'll talk about the memory optimization and how we can store more data in memory in a more efficient way, i.e. fragmentation. And once we design a cache, we'll talk about the combinations with scaling the cache and things like cache misses, cache invalidation, method congestion, etc. So if you want to learn more about these concepts, make sure to keep watching and let's get to the designer. High level, our cache would look like this. They would receive key and value. Then we would compute a hash function on the key, then define what bucket that item belonged to. And in the single bucket, we can have either one item, as you can see on the screen, or it's also possible to have multiple items. To make it work, we need to make sure we define two different methods. The first one is a hashcode function, and the other one is an equals function. Hashcode will be used to find the bucket on where the item is located, and equals function will be used to find that item in the same bucket in case we have a collision and we have multiple items under the same bucket. As you can see here, bucket number 7, we have multiple items, so we'll need to maintain some sort of data structure, for instance, a tree, that would give us log n search time for a specific item based on the equals method. On top of the hash table, we'll need to maintain an additional data structure, which is double linked list. And we need it to make sure we can support LRU cache, which means least recently used. So every single time we read from cache, for instance, we would move the item that was read from wherever it's located in the linked list to the head of it. So this way, the items that are not used would end up in the tail of the linked list and then eventually be removed or evicted from the cache. If you want to learn more about how it's implemented with the data structures, you can go to the neat code and find the problem that is called LRU cache and implement it yourself in whatever language. Now moving on to the memory. So we need to store a lot of different items in the random access memory, or RAM. And there are common problems that always happen there, which is fragmentation. And given the fact that we'll maintain a lot of different items in the memory and they'll be read and removed at a random time, we need to make sure we optimize the memory utilization. To understand the fragmentation, we need to understand on how data is written and read from the main memory. And it's done with pages. There is a memory pages, which is the minimum unit of data written or read from the memory, which means that if, for instance, the page size is 1 megabyte and we write 10 megabyte file, there's going to be 10 pages written to the memory. And if the file is 10 bytes and the page size is 1 megabyte, then the whole page will be utilized to store only 10 bytes. So we'll waste almost the whole megabyte of memory to store 10 bytes of data, because the page is the minimum unit of memory that we can deal with. So to optimize our memory utilization and reduce fragmentation, we want to make sure that our cache items as close as possible fit into a single page. It means that if file is, for instance, 100 kilobyte, we want to make sure that the page is 100 kilobyte. And if the file is 1 megabyte, we want to make sure that the page is 1 megabyte, so no memory is wasted. So the way we're going to do it is by adding a notion of a chunk. So as you can see on the screen, a chunk is a small chunk of data inside the page. So what we do, we're going to define our page size, let's say 1 megabyte or whatever number we want. And then inside every single page, we'll have a big multiple chunks. Now, let's say if we have the page size up to 1 megabyte, we can say that we want to have 30 or 40 different sizes of the chunk. It will mean that if, for instance, our chunk size is 100 kilobytes, then only 10 chunks can fit inside the same page. If our chunk size is 1 megabyte, then only one chunk can fit inside the same page. This way, we have 40 different classes. And as we get new items, as the cache item is created, based on the size of the item, we can put in the right slab of memory. So we would have 40 classes of memory slabs, and they would all differ by the size of the chunk inside the page. This way, as we store the records, we compute the item size, and then we know what memory class we want to put it in. Every single class would allocate page to store data inside. As you can see here, for instance, we would have slab class 1, which would say be size of 72 bytes per chunk. So we would have almost 1,500 chunks per page. And then the maximum size of the chunk would be 1 megabyte, and that would be called Slack class 43, for instance. So now, as you receive items to store in cache, we would compute the size of them and let them put them in the right class of memory. This way, we have a generic approach where we have multiple classes, and then every single Slack class would have a page allocated separately from the main memory for utilization. For instance, over here, you can see that in Slack class 1, we only have one chunk of memory taken. The other chunks are free, so we are not going to allocate an extra page for this class. But if it's class 43, which is the size of 1 megabyte, then the moment we store a chunk of data, we automatically allocate a new page from the main memory, so it's ready to store more records. So you would allocate memory based on the demand for the specific slab class. Now, as we've covered the memory model, let's see how the actual data structures can fit into our memory model. So as you can see on this screen, just to recap, we have multiple slab classes from 1 to n. They all differ in the chunk size. Slab class 1 would have the smallest chunk size, and in our case, class 43 would have the largest chunk size. Now we have a hash table that will consist of the key and value. Our key would be the actual key that is supplied by a client. The value would be a link to a node object or a linked list object that would store a cache item. So this way, every single list item would be connected as a double linked list between each other. As you can see on the screen, for instance, as we write data sequentially and don't read from our class 1 slab, then all the items would be sequential. They would be sequentially represented in memory as well as in the linked list. But as we start accessing those items, we would keep moving them into the front of the linked list and change the structure in our slab class walk. So this way, we would have random links between different items form a single linked list. As we remove items, then we would remove that item from the linked list, and in the memory, we would get a free square somewhere in the middle or somewhere in the page. That can be tracked, and as new data comes in, since this size fits this class, that new data can fill in the empty spot or chunks that were removed from our pages. This way, we can improve fragmentation dramatically because every single time we remove an item from the cache, we are going to remove a chunk inside the page. And the chunk can later be used by a new item that is stored in the cache. Now let's talk about the read and write workflow. Let's start from writes because it's the easiest one. When we write data to our cache, first, as we receive key and value, we compute the hash of the key. Once we know the hash of the key, we identify the bucket where the item has to be stored, and then we create a linked list node item that will consist of the key and value. That item will be placed inside our chunk, inside our page. So the value of our hash table would be a link that points to a memory cell in the RAM. So as you can see on this screen, the yellow would be a link, and a cache item that will consist of key and value will be stored as a linked list node inside the chunk, inside the page. And as we write data, we'll also maintain a double linked list connections between the node items. So over here, all of them are sequentially connected just because, let's say, we wrote 5 items and none of them were just read yet. When we read data from the cache, it gets a little bit more complicated because we can get a collision, meaning that multiple keys can have the same hash code. In this case, as you can see on the screen, there is no collision. We receive key and value, we compute the hash code, we find the bucket, and then there's only one link to a single cache item under that bucket. So we know exactly where the cache item is located in memory, and we go right in there and find it. If we have a collision, it means that we have multiple cache items under the same bucket. So this way, these multiple items would be stored in a tree, and we would use binary search or some sort of Login search algorithm to find an item that has to be returned back to the client. To find that key, we would need to go through the tree and compare the requested key with the tree node's keys until it matches. Once it matches, we know for sure that this is a link for the object that is requested. The next topic I want to talk about is locking. Because every single time we read an item, we need to move a cache item in the linked list from where it's located to the head of it. And that requires locks because we can't just move multiple items at the same time without breaking up the structure of the linked list. So every single time that move happens, we need to lock the linked list. And this locking operation reduces the performance of the cache dramatically. So what we want to do is find a way to optimize this. So there are multiple ways we can apply here. The first one is that we can maintain multiple linked lists per slab class. This way we partition the linked list, and now if, for instance, there is a high demand for reads in the slab item 1, it doesn't impact the other slab class because they have different blocks. The second thing we can do is make updates to the linked list in a period of time. For instance, we do it every 60 seconds, which means every 60 seconds, we would use a lock on the linked list and move multiple items at the same time instead of moving them one by one. This way, we reduce the number of flags that need to be issued on that linked list and simplify and improve the performance of the cache. The third thing we can do to improve the locking is splitting our cache into multiple categories. For instance, we can have a hot cache, items that are frequently accessed. We can have warm cache and cold cache, and have different workflow on how item can travel from the cold cache all the way to the hot cache. And we can have different mechanisms of updating the location of the items after their access. For instance, in the hot cache, since it's very often accessed, we are not going to update the locations of the items in the real time. We would just read and remove any kind of logs from there. But in the cold cache, obviously, those items wouldn't be accessed that often, and it would be a subject for eviction items from that specific linked list. So for instance, we can have 3 different linked lists, which would be hot, warm, and cold, and have a maintenance thread, for instance, that would periodically scan them and move items between different states. What we achieve is that, for instance, if the item is hot, there are no locks on the hot list. And this is it for this video. So first we've covered the data structures, then we talked about the memory model, the read and write workflow, and then talked a little bit about the locking. So this is the basic implementation of the LRU cache that we can implement ourselves. And if it's asked from the system design interview, you can just use this as an example. With that, I hope you found this video useful. If you liked it, make sure you subscribe to the channel and put a like there. And I'll see you in the next one. Bye.